Are these your slides? I think you should see your slides now. Do you see them?
Yes.
Okay, we're ready for you whenever you are.
Hi.
Go ahead.
Okay, so this is Corina Pasareanu from NASA Ames, and David Hall, also from NASA Ames, is also here. And our presentation is about automated design time analysis for the GOES system. Next. So GOES stands for Geostationary Operational Environment Satellites, and these are satellites operated by the National Oceanic and Atmospheric Administration. Their goal is to provide continuous weather imagery and monitoring of meteor and space environment data, and to protect life and property across the United States. Next. And GOES is the next generation of these satellites, and they are developed in collaboration with NASA. And the goal of GOES is to provide continuity of the GOES satellite, and at the same time to improve the remotely sensed environmental data. And these systems are software intensive. Of course, they must be extremely reliable and correct. And they consist of many interactive components that cause of challenge to verification. So we thought that these systems would be a good case study for our tool. And this is what this talk is about, our preliminary analysis of parts of such. Next. So testing is the typical technique used for software reliability. But this is often manual and time-consuming, and typically used late in the software life cycle after the code has been written, when it is expensive to be fixed and the discovered interaction error. Next. So we advocate systematic analysis of design time before even the code is written, and this is in a broader context of GOES, but we will make our presentation on how one can apply this to GOES. So our goal is to identify and correct errors of design time when it is easier and more cost-effective to do this. And even if the system is already implemented, we believe the behavior identified from the design specifications can be used to guide the testing and also to assess the completeness of the test case. So similar to the previous talk, one can also assess completion, things like that. So next. So our analysis approach was to take the state transition behavior, which was informally described in the GOES document. So we took these descriptions for a portion of GOES that concerns the ground segment, and we translated it into the MathWorks Stateflow notation. And the reason for this translation was that we found that there is a natural mapping between the GOES informal design documents and the Statechart formalisms. And then we used Polyglot, which is a tool that we have developed here at NASA Ames, translate these Statechart models into an internal representation that is amenable to formal verification and also to automated testing, and I will talk more about it. And we performed the analysis using an open source verification tool set that we have developed at NASA Ames, called JPF. And in the next slide, I will describe all these components in more detail. Next. So, first of all, what is Polyglot? This is an extensible framework for defining describing different semantic variants of Statechart. And we developed it in collaboration with the University of Vanderbilt. So the tool provides modeling and analysis for multiple Statechart formalisms. Also it is designed to capture complex interactions between components. And it is based on a formal semantics that captures different variants of Statechart that we developed to make sure, that we build that our analysis is correct. And the tool is freely available from the link that is provided from University of Vanderbilt. Next. So at a high level, the tool takes different models written with different kinds of Statechart formalisms, for example, Stateflow and Rhapsody, and it imports them into a common representation. And this is translated into a Java representation of the state machine models, and we also formally specify properties of these models. And then the framework basically provides a generic execution environment that allows one to analyze these components that perhaps were developed by different teams using these different kinds of formalism. So our goal was to provide a common environment for the analysis of this kind of heterogeneous components that perhaps are built in big projects where several teams work on different parts. And distinguishing feature of our framework is that we have this pluggable semantics. So the syntax of the models, meaning the states and transitions, are kept separately from the semantics that actually tells you how to advance the transitions and so on. And you can even change the semantics. So let's say if I have a Statechart, I can plug in a spatial semantic or a Rhapsody semantic and see if there are any differences in the behavior of the models. And this again can help in porting components from one project to another and so on. And as I said, this is the internal representation is actually Java, and then we feed it to Java Pathfinder with this JPF tool that we have developed over many years, more than 10 years now. So it is a mature tool that is designed specifically for analyzing the Java code. And we have had several papers describing this Polyglot tool that appeared at ISSTA, NFM, and other conferences. Next. So how would one use this Polyglot tool? As I said, the user defines only the structure of the Statechart, meaning the state transition, the different parallel state machines. And then there is a separate component that provides the pluggable semantics. It can be selected from a defined set. And we also provide temporal properties using a pattern-based system to facilitate formulating properties that one would want to check over such models. And the analysis can be performed by simple simulation, so you can simply run this model, or with Java Pathfinder, which at its core is an explicit state model shaping. And we also have a component called Symbolic Pathfinder, which performs a symbolic execution of these models and does basically a systematic exploration of all the paths through these models, and it generates automatically test cases or test inputs or test sequences that are guaranteed to provide high coverage through these models. And both Java Pathfinder Core and Symbolic Pathfinder are available from this website. Next. So just to labeled with S1, S2, and so on, and then transitions that allow you to go from one state to another under certain events and certain conditions. And for example, for the single state chart, event T here is if event T occurs, leads to S4 in the UML semantics, S5 in the Rhapsody semantics, and to S6 into the Stateflow semantics. And the reason is because although the Statechart looks similarly under all these different semantics, under all these modeling tools, they behave differently. So, for example, in Stateflow, these outer transitions have priority over inner transitions, while in UML, transition actions are evaluated at the end of a transition path, so this is a transition action, while in Rhapsody, this is evaluated immediately as it is encountered, so that's why this transition. So this is just to give you an idea of the tricky details that we need to take care of in order to build our tool. So next, please. So we made a design choice to use Java as a common language representation, and there are several reasons for doing so. So the first one is that Java provides an executable representation for the model. So this allows for a quick validation and debugging. Also, Java, of course, enables modular and extensible design for Polyglot. So not only we use Java as a common representation, but Polyglot itself is written in Java. And of course, one of the main reasons is that we could leverage our mature analysis tools, JPF and also SPF, for automatic test case generation. And another reason is that there is a large action language for this kind of Statechart formalisms that can be mapped quite easily into Java. Next, please. So I will talk a bit about property specification. So Polyglot allows, I think you, yeah, okay. So basically, we provide, we use the property patterns developed by Wire and others, and basically these are English language patterns that help the users formulate the requirements of the model. So each property consists of two pieces. One is the scope, which says when the property should hold, and another is the condition that should be satisfied. And I will give you an example of such property. And this has been implemented as a graphical extension the modeling tool. So, for example, we have such a graphical extension into engineering Stateflow. Next, please. We have 5 patterns in 2 groups. We can specify actions, for example, that an event never happened, or universality, for example, that it is always the case that some invariant, desired invariant holds. Also existence, that specifies that a certain event in our model or a certain state happens at least once. And there is also this order that you can specify, so you can have precedence, which says that the state must precede another, and also response, which says that the state must follow another. And we found that these kind of patterns are necessary for reasoning about Statechart, where you typically, just assertions or preconditions or post conditions are not enough, because you need to reason about the continuous behavior of your model and to relate different states at different times of the execution. So this is why we introduced, we use these pattern systems. And next, please. So I will talk now a bit about the analysis. So So recall that we built these Stateflow models. We use Polyglot to translate them into these Java representations. So now we can perform the analysis using JPF or SPF. And I'll focus a bit on Symbolic Pathfinder, which is our tool that performs systematic test case generation. So unlike, for example, in the previous talk where we heard about random testing, here we try to do systematic traversal of the path to the model. We also collect the constraints imposed by the conditions in the models, and then we solve those constraints using off-the-shelf solvers, and the solutions provide the test vectors for the model. And you can imagine you can also use the test vectors for the code that is written based on those models and so on. Next, please. So at a high level, Java Pathfinder is a verification tool set. It started as a so-called explicit state model checker for Java, but it has evolved into a very rich verification framework that allows different kinds of analysis for Java. So in this system, one provides the program, which is, for example, Java bytecode, and also configuration, and perhaps a set of properties. And then the system tries to go systematically through different behavior of the code, also through different thread configurations if multi-threading is available, and then it produces a verification artifact, which can be an error report and also a phrase, showing how the error is fixed, and that just can be used for debugging. Also, in the case of Symbolic Pathfinder, it will produce a certain set of test cases and also a report of the coverage obtained, which is monitored using this generation, and so on. So, as I already said, typical uses are software model checking, which are used for detection of deadlocks, traces, and the search error. And the symbolic execution expression, Symbolic Pathfinder, is typically used for test case generation. Next, please. So, a bit more details about Symbolic Pathfinder. So this is an extension of the JPF core, and it takes us into the Java program, and then it goes systematically to the code. It basically builds a symbolic execution tree to the code that shows all the possible paths to the code and the constraints associated with taking different paths. And the tool interacts with off-the-shelf constraint solving to solve these constraints, and the results are test sequences and also error reports, because while generating these test cases, the tool also checks for if the specified properties are satisfied, or if maybe there are some exceptions thrown, and so on. And we have several publications on it, and I think I already talked. I gave a high-level overview of it, so we can move to the next slide, please. Yeah, so the tool is available. So as I said, both Symbolic Pathfinder and actually the whole JPF framework is open source and freely available, and this is the link for the tool. Please go to the next slide. And now how this is interacting with the Polyglot. Basically, we can run the Polyglot framework inside SPF, and the idea is that SPF will guide the execution of the Statechart along different paths. And also the symbolic execution tool can generate input data, and this can be used to simulate the Statechart in the Polyglot tool, and also to generate test vectors that would allow you to simulate models in their original environment, for example, in MATLAB for Statechart. And also we generate these reports, which are test vectors, and property reports that can be inspected by the developers, and they can correct their models and so on. Next, please. We have applied our combination of Polyglot and JPF to a variety of applications. So one is the analysis of an arbiter module for the Mars Exploration Rover. And we also looked at the interaction between the RF launch vehicle and the Orion crew exploration vehicle. And we reported this in some papers at ISSTA 2011 and also NASA formal method in 2012. So my point is to tell you that these are becoming pretty mature tools, and this is why we thought, we wanted to look also at GOES-R and evaluate these tools. So next, please. So going back to GOES-R, what we did, we modeled several portions of the ground segment using Stateflow. And for example, I give here some statistics for some of these components, and the number of states, and we also have parallel state machines, and the number of transitions, and the number of Java lines of code that were generated. I should add that this is an ongoing process, so we would like to extend these models and together with the GOES-R developers to enrich and investigate what kind of issues need to be modeled and analyzed. Please go to the next slide. So this is a very simplified model of one of the GOES-R components that specifies two parallel state machines. And also here we show an absence property, which basically says that globally it is not possible to be in state degraded and also for a command to be zero. So just to give you a glimpse of how the interface to the user would look for our analysis tool. And once you specify this property, basically you can use Polyglot with Symbolic Pathfinder to analyze this property over all the possible combination of behaviors in this Statechart, and also to generate test cases. So next, please. So in particular, we performed some analysis of some of these models. So for example, for a larger model, we ran the analysis up to some specified steps, for example, 40 transitions on each run. And this results in a certain number of test cases. And we also test properties such as the absence property that I showed you, where we state that the model should never be state degraded if the command is online. So this is a property that we thought makes sense for the models that we analyzed. And this property holds for the model that we analyzed. So please go to the next slide. So I will close by saying that we would like to expand and robustify this tool, meaning Polyglot, in conjunction with the analysis that we provide. And also for the components that we model, we would like to use compositional verification for increased scalability. And we have done some work in the past. Basically, this work tries to analyze each component in isolation and then to compose the results without analyzing the whole system as a whole, which can be very expensive. And furthermore, we like to identify and analyze more properties of the ground system. And we also have idea about taking conformance to different levels of abstraction. So in those are documents, there are diagrams that several levels of details, and we believe there is a relationship, a formal relationship between different levels that we can check automatically. And of course, we can also use their test to measure coverage, obtain, and maybe increase the coverage using our tools and so on. So this concludes our presentation, and now we are waiting for a question. Thank you.
All right, are there any questions in the room?
Hi, so I have a question about Java Pathfinder. So it's my understanding that Java Pathfinder can also model code directly and like that. So I was wondering what the advantages of pouring Statechart representation versus modeling that through Java Pathfinder versus modeling code directly through Java Pathfinder.
So it was very difficult to understand the question here. I'm not sure what could be done to improve the clarity.
Yeah, could you repeat? Sorry, we cannot hear you very well. So it's related to Java Pathfinder, but
Yeah, okay, so maybe is that better?
Go ahead.
Okay. So my question is related to Java Pathfinder and your use of it. In your presentation, you said that you create a Statechart representation of the code you're testing and then run that through Java Pathfinder. But it's my understanding that Java Pathfinder can analyze code directly. So I was wondering if you could talk about the advantages of using the Statechart versus analyzing the code directly in Java Pathfinder.
yeah, okay. So the question is, why don't we analyze the code directly? Is Java Pathfinder can analyze the code? No?
That's right.
Yeah.
Of course, Java Pathfinder can analyze applications written in Java. But the point is of this talk is that through this Polyglot work, we have extended the applicability of Java Pathfinder to also different models, and not only through translation of one particular formalism, but we could even analyze systems that are built from models that run different semantics, and analyze their interaction early. So I understand it was a good question, but and we do perform analysis of Java programs for other applications. But in this particular talk, we wanted to highlight that now we can also analyze models.
Are there any other questions in the room? I have about 2 minutes. I will take questions on the phone if there are any.
Thank you. Again, if you'd like to ask a question from the phone, please press *1. Question for Mary.
Go ahead, Mary.
Yeah, hi, Mary. It's Mary. I'll make this quick, and it's really more of a comment. Just going back up into your presentation, you were looking at some systematic design time analysis, and during there, you were looking to correct errors at that point in time, and I'm sure we're all familiar with the sooner you could identify the error in the software during the software life cycle, the more significant the cost savings are. In other words, when the errors are caught later, the exponential cost of fixing those errors and the labor involved goes up exponentially. And I was just curious because I know this was a hot topic at our last IV&V seminar. Are you trying to assess some dollar values to that? And if not, maybe that's something you might want to keep in mind. I know sometimes it's kind of hard to quantify and put a dollar value, but I think if you can, that would be a very powerful metric to have.
Yeah, so thank you for your comment. Indeed, this is our motivation, that we want to do as much analysis as possible at the design time when it is much cheaper to detect and fix these kind of errors. And yeah, it would be great to put some dollar amounts on this. That would really help our case. I think we have some data points from some reports, but we should definitely work on it. A very good point. Thank you.
Thank you.
Okay, if there are any remaining questions, we will take those in the breakout session. Thank you, Corina.
Thank you. Bye.
And make sure you know where to, do you know where to go, Corina, for the breakout session online?
Sorry.
Do you know where to go
Okay,
online?
thank you.
Okay, thank you. Charlie, are you on the phone?
Yeah.
All right, we are